All right, so this is section 15.9, video 2. This is going to be a little bit strange because I already know that I'm going to be doing 3.5 examples in this one. And then in my last video, I'm going to do 1.5. I'm basically going to finish the one that I don't finish in this one and finish it in the third video as well as the last problem. So a little bit strange in the fact that I already know that, but all right, so let's go ahead and do some examples. Now that we know our conversion factor to get the spherical, we can go ahead and do some triple integrals. So first one's pretty straightforward. Use a triple integral to find the volume of a sphere with theta ranging from 0 to 2 pi, phi going from 0 to pi, and rho going from 0 to r. So the way I typically set these up is I usually put phi or theta on the outside. It doesn't really make any difference which one in this case because they're both constant bounds. But again, I usually do it as, I think I usually do it now that I'm thinking about it as theta and phi, but I'm going to do it a little backwards in this one. So I'm just going to go in the order exactly the way they have it written in the problem. So 0 to 2 pi, that's theta. 0 to pi, that's phi. And rho is going to go from 0 to r. Now don't forget, we are trying to find the volume, so I don't have any kind of an extra, and as much as I hate to say it, it's rho, but I don't have a density function, which we usually call rho. I don't have an extra density function here, so we're really just taking the antiderivative, or excuse me, the integral of 1. But we do have the conversion factor, which was rho squared sine phi. And then you have to follow the order that you just wrote your integration in. So it's d rho, d phi, d theta. I think I usually do theta and then phi, but I just did it in the order that they have it here. So, okay, so let's go ahead and start the antiderivative process. Can't split these up, at least not yet, because 0 to r is not a constant bound. So we can't do that part yet. So we can just do it as it stands. Antiderivative with respect to rho is going to be 1/3 rho cubed sine phi evaluated from 0 to r d phi d theta. All right, so let's rewrite our couple integrals here. Let's plug in r for rho, so we get 1/3 r cubed sine of phi. And then if you plug in 0 for rho, you get nothing out of that. So that's done. Now let's see. So we can split the r's, we can split the phi's. I'm sorry, we can split the thetas and the phi's. There are no thetas. R in this case is just a number basically. It's not a variable in this case. It's just like a number. So I can do, technically I can pull 1/3 r cubed out to the front and then do the integral from 0 to 2 pi of d theta times the integral from 0 to pi of sine phi d phi. Okay, we have done the integral from 0 to 2 pi of d theta enough times. We should know by now that that is 2 pi. And then we actually have to do a little bit of work here. So that's going to be, antiderivative will be negative cosine of phi from 0 to pi. So we get 1/3 r cubed times 2 pi times, plugging in pi. So cosine of pi is -1, but the negative out in front is going to make that a +1, minus, plugging in a 0, cosine of 0 is 1, but the negative out front makes that a -1. So that 1 minus -1 really becomes a 2. So what we get is 1/3 r cubed times 2 pi times 2. So 2 pi times 2 is 4 pi, so we get 4 pi thirds r cubed, or you're probably used to seeing it as 4/3 pi r cubed. Very nice. That is the volume of a sphere. All right, so let's move on. we want to evaluate the triple integral over h. Notice the change there. I called it h because it's no longer a, I guess, one-dimensional region, but maybe h is because it's over a what they call a hemispherical region. So it's not like a box, because maybe like the box is like the E. I'm actually not sure in this case, to be honest with you, but I think it's H just because it's over a hemispherical region. Let's see, and it lies above the XY plane and below the sphere, x squared plus y squared plus z squared equals 1. So that one's really not too difficult, I guess, to sketch. So we get an idea of what we're looking at here. So it's going to be the top half of a sphere, basically. And because it's going to sit, it says above the XY plane. So your circular part is going to look something like that. Then you're going to have the top half of a circle, something like that. I guess that's probably the best way to do it. And then you could, if you want to, you can kind of draw the outside of the sphere going like that or something, just so you can get somewhat of an idea that that's spherical. And this value up here is 1, which makes that a 1. It makes that a 1. All right, so there's our sketch. So let's see, how are we going to set this thing up? Well, pretty clear to see that theta, which is this part, goes all the way around. So that's going to go from 0 to 2 pi. So we know that theta is going to go from 0 to 2 pi. So I'll put my d theta on the outside. I know that phi starts from the z-axis and opens up the angle of Bloom, and it's only going to go down to the xy plane. So it can only go a distance of pi halves. So my angle of Bloom is going to go from 0 to pi halves. That's d phi. Probably going to need to leave myself a little more room than that. I'll put d theta out here, then d phi out here. And then my rho goes from the center out to the edge. Well, anywhere out to the edge right here is a distance of 1. So rho goes from 0 to 1. So there is my d rho. We also have to have our conversion factor, which is rho squared sine phi. And we have to convert x squared plus y squared into spherical. You can do it in multiple ways. It might be easier to say, first of all, well, x squared plus y squared is r squared in cylindrical. And why might that be easier? Well, because I actually have a formula for r in spherical. R was rho sine phi. So if I square that, I'm going to get rho squared sine squared phi. So I have a rho squared sine squared phi. Ooh, just left myself enough room. Good thing I moved it in the beginning. So that's what we have to take the integral of. All right. The good news is, I believe all of this can be separated because I've got all constant bounds. Everything is a multiple on the inside, which can be separated. So we can go ahead and separate all three of these integrals. So let's see, d theta, well, there's no thetas at all. So we're going to get an integral from 0 to 2 pi of d theta. And we know what that one is. We're going to get the integral from 0 to pi halves of, let's see, I've got a sine squared times a sine, all of phi. So that's going to be sine cubed of phi, d phi. And then it looks like for rho, I'm going to have a rho to the fourth. So 0 to 1 of rho to the fourth d rho. So the first one and the third part are not going to be terribly difficult. The middle one's going to create a bit of an issue, something that we really haven't dealt with. So it's probably good that we're doing this one. So we know that 0 to 2 pi of d theta is 2 pi. That's easy. We know that we can take the antiderivative of the rho part. That's 1/5 rho to the fifth from 0 to 1. Plugging a 1 in there, you get 1/5. Plugging a 0 in there, you get nothing. So I know I'm going to get a fifth out of this one. So I'll bring the 2 pi down. It's the integral in the middle that's going to cause a problem. We can't, unfortunately, use some kind of a power rule. So we have to do some kind of a reduction. One thing we can do is we can change sine cubed to be sine times sine squared. So I can write it as sine of phi times sine squared of phi d phi. And why would we want to do that? Well, because now we have a property that we could change sine squared into 1 minus cosine squared. This goes back to higher order trig integrals. Oops, that should be a phi. Higher order trig integrals that we did as something that's technically not covered on your AP test. All right, so now what are we going to do with this? Well, now what we need to do is we need to do a U substitution. The composited piece here, or the most composited piece here, is actually cosine of phi. Technically, 1 minus cosine squared is a composite piece because it's within that parentheses, but the cosine phi is actually even more composited because of the fact that it's squared. So U is going to equal cosine of phi. And then we can do the U substitution process and watch the magic happen. So du is going to be negative sine phi d phi. Solving for d phi, we get du over negative sine of phi. So I am going to combine my 2 pi and my 1/5 just to kind of get those out of the way. So that'll be 2 pi fifths integral sine phi 1 minus u squared, and my d phi becomes du over negative sine phi. And the wonderful thing is the sine phi's go away, so it's going to leave me with a negative sign, which I can pull all the way out to the front. I'm going to have negative 2 pi fifths. Because I really don't feel like changing back, I'm going to change the bounds here as we go. So if I plug 0 into phi, cosine of 0 is 1. If I were to plug pi halves in for phi, cosine of pi halves is 0. 1 minus u squared du. And if you don't like the fact that the bounds are flipped, you can use the negative from the front and multiply or get rid of the whole thing by negating it. So really what we have is 2 pi fifths integral from 0 to 1 of 1 minus u squared du, properties of integration. So let's go ahead and finish this off. We'll have 2 pi fifths. Antiderivative is going to be u minus 1/3 u cubed from 0 to 1. Fortunately, the 0 will make all the u's go away, so let's just plug the 1 in and see what we get. 2 pi fifths, 1 minus 1/3, which is 2/3, so we get 2 pi fifths times 2/3, which should be 4 pi over 15. And because this one had an actual density function that we have just found the mass using spherical coordinates. All right, moving on. Triple integral over e of z dv, where e lies between the spheres x squared plus y squared plus z squared equals 1, and x squared plus y squared plus z squared equals 4. It would be really nice if we didn't have that extra density function, because then we could just literally find the volume of the two spheres and subtract them. Unfortunately, we can't do that in this case because we do have a density function and it's variable. It's not like it's a constant density function, because if it was constant, then we could still do the same idea and just multiply it. But here's what we're looking for. Oh, and it says in the first octant, if I didn't read that part already. So this is what we've got. We've got a sphere with a radius of 1, and we've got a sphere with a radius of 2. So here's 1, and here's 2. So what we've got is, I guess the best way to draw this is just to kind of draw spherical pieces like this, curved or whatever, something like that. And it is connected here, there, and there. So basically, we're talking about what is the mass in between those two spheres, in between those two spherical pieces. So drawing that helps because I know that theta goes from 0 to 2 pi. I'm sorry, 0 to pi halves, not 2 pi. So that's going to be my d theta. Phi also goes from 0 to pi halves. So there's my d phi. I defy you to figure this one out. And then we know the radius. Now the radius is in between the two spheres, so it's going to go between here and here. So the radius goes from 1 to 2. And that's my d rho. Don't forget you've got your conversion factor, rho squared, sine phi. And we have to change z into terms of spherical, and z was rho cosine phi. So we're going to plug rho cosine phi in. All right. Once again, this one's not terrible because of the fact that all bounds are constant and everything is separable. So let's go ahead and separate these into 3 separate intervals. 0 to pi halves of d theta, because there are no other thetas, times 0 to pi halves. Let's see, for phi, we've got cosine phi, sine phi, d phi. And then for rho, we've got 1 to 2, rho cubed, d rho. So once again, the first part and the last part are not going to be difficult. Now in this case, for theta, we're only going from 0 to pi halves. So I'm sure you've probably guessed it. Instead of 2 pi, that's going to be pi halves. So that part will be easy. And if for whatever reason you're not understanding or not getting the gist of that one, take the antiderivative, you would get theta, plug in pi halves and 0, you would still get pi halves. For rho, it's going to be 1/4 rho to the 4th from 1 to 2. Now we do have to plug a couple things in here to see what we get. Plugging a 2 in, 2 to the 4th is 16. So you're going to get 1/4 of 16 minus 1. So that's going to be 15/4. So I'm going to have the pi over 2 and the 15/4. Once again, we're going to have to do a little bit of a u substitution in there. We've got cosine of phi, sine phi for the middle one. So let's do a u substitution. In this case, it actually makes no difference which one you do the u substitution for, because the derivative is going to get rid of the other one. Personally, I like to pick sine because at least the derivative is positive. So du will be cosine of phi d phi. So d phi is going to be du over cosine phi. So let's go ahead and make our substitutions. And I will change the bounds here. So let's see, I'm going to get cosine of phi times u times the new d phi, which is du over cosine phi. Those will go away. Changing the bounds, plugging 0 into sine is 0. Plugging pi halves into sine is 1. So then we're going to have the integral from 0 to 1 of u du. So we're going to get, we're going to get 1/2 u squared from 0 to 1. Plugging in the 1 gives me a half. Plugging in 0 gives us nothing. So I'm going to bring down the pi halves. I'm going to bring down the 15/4. And it does not look like anything is going to cancel out. So it looks like we're going to get 15 pi 16ths. And that should be the mass in between those two spherical pieces in the first octant. All right, I am only going to start this next problem and I'm going to finish it in the third video because the video is running a bit long here. Trying to keep them all under 25. All right, so let's find the volume of the solid that lies above the cone phi equals pi thirds, and below the sphere rho equals 4 cosine of phi. Okay, first thing we might want to do is sketch this. Whoops. Okay, I didn't mean to do that. There. All right, so let's go ahead and sketch this thing. So the sphere, rho equals 4 cosine of phi, is actually a sphere which sits up on top of the xy plane, and it's got a radius of 2. So it's going to look, I guess, something like this. Something like that. I'll make it actually look like a sphere. So it looks something like that. And then we've got this cone, phi equals pi thirds. Remember, phi is the angle of Bloom from the z-axis. So basically that means it's going to come out pi thirds from the z-axis. So it's going to look something like this. And then obviously it's going to be circular on the top or whatever, but that's basically where the cone is going to extend from. So it looks something like this. It's going to keep on getting bigger and bigger. But what we're looking for here is the volume of the solid that lies above the cone and below the sphere. All right, so we're going to have to do a little bit of work here. So we've got rho equals 4 cosine phi. We also know that z equals rho cosine phi. And if we want to put that in solving for cosine phi, we know that cosine phi equals z over rho. So how might you ask, did I know that this sphere sat on top of the xy plane and was a sphere of radius 2, which has basically been shifted up from the origin 2 units? I am so glad you asked that, and that's kind of why I gave you these pieces that I gave you up there. So what I'm going to do is I am basically going to solve this thing and figure out where it is, putting it back into Cartesian, actually. So the fact that I just solved for cosine of phi, and that's z over rho, I'm going to replace cosine of phi in this equation, rho equals 4 cosine phi. I'm going to replace the cosine phi with z over rho. So if I multiply both sides by rho, you get rho squared equals 4z. Well, rho squared in Cartesian is x squared plus y squared plus z squared equals 4z. Okay, if I subtract the 4z over to the left-hand side, I get x squared plus y squared plus z squared minus 4z equals 0. So what I can do is I can take the z stuff and I can complete the square. So what we're going to get is x squared plus y squared plus, and then z squared minus 4z equals 0. And what do I have to put in there to complete the square? If you remember completing the square, you take the middle term, which is the negative 4, divide it in half, and then square it. So negative 4 divided in half is negative 2, squared is 4. but I can't just arbitrarily add a value to one side of the equation without adding it to the other side of the equation. So what that gives us is x squared plus y squared plus, factoring that, and this is the reason for completing the square, is z minus 2 squared equals 4. So what that is, now that is a standard equation with a sphere where the center is 0, 0, and 2. Remember, it's been shifted now up 2 units. That's what the z minus 2 is. And the radius is 2. All right, and that's where we are going to stop that one. And we're going to come back with the third video. We will finish this one off and one more problem.